In our last notes, we talked about all the different kinds of bonding, and we're going to start this unit off with a focus on ionic bonding. So to start these notes, we're going to do a little reviewing about what happens in an ionic bond. So the first thing that happens is that the metal atom, the one on the left-hand side of that staircase on our periodic table, and remember, metal atoms have low electronegativity and low ionization energy. So what they're going to do is they're going to transfer all of their valence electrons to a non-metal atom. So they're going to give away their electrons. So we see here in the picture, sodium has one valence electron that he is going to give away. All right, he's going to transfer it to a non-metal atom. So when he does that, this metal atom here, this sodium, is going to become positively charged. Okay, so he's going to be sodium with a +1 charge because he had lost an electron. So now he has more protons than electrons. The second thing that happens is that non-metal atom, the one with high electronegativity, high ionization energy, the one on the right-hand side of the periodic table, has to accept those valence electrons that metal atom wants to give away. So as soon as that non-metal atom accepts the electrons, it becomes negatively charged. So we see here the chlorine atom. Remember, chlorine is a non-metal on the right-hand side. He is getting an electron, this electron right here, from a metal atom. And now he, instead of having 7 valence electrons, he now has one extra. He has 8 valence electrons. So chlorine is going to have one more electron than protons, so he becomes a -1 charge. Finally, the electrostatic force, remember the attraction of positive to negatives, is going to hold these atoms together in an ionic bond. So that's how we get sodium and chlorine to bond together. Sodium is going to give its valence electron to chlorine. Now sodium is a positive ion, and chlorine is a negative ion, and because opposite charges attract, they are going to hold themselves together, okay, as in an ionic bond. All right, we're going to dissect the example of sodium and chlorine coming together to make sodium chloride by looking at the number of valence electrons and the oxidation number, or the charge, before and after bonding. So we can see exactly what happens and why they need to make a bond. Okay, you're going to want to stop and actually draw this picture into your notes and a little table that kind of looks like this. What we're going to do is we're going to analyze the number of valence electrons and the oxidation number for sodium before and after the bond, and chlorine before and after the bond. So take a minute to pause the video and draw the pictures and draw down this table. All right, so let's take a look at sodium. Remember, sodium is on the left-hand side of our periodic table. He is going to have low ionization energy, right? And he's going to have what's called low electronegativity. Because he has low ionization energy, it's not going to take on a lot of energy to take an electron away from him. So he's going to be very easily transfer or give away one of his electrons. So that's what he's going to do. So before he gives it away, he has 1 valence electron, and after he gives it away, he actually has 8. Okay, and let me explain why. When atoms lose an electron, that valence shell goes away. Okay, and so what you have underneath is a new valence shell, and in sodium, it's this shell with 8 electrons in it. All right, so after sodium gives away his electrons, he now has 8 valence shells, or 8 electrons in the valence shell that's lower. All right, and so let's take a look at the charge before and after. Now the oxidation number is also what's called the charge of the atom. Now before sodium bonds or gives away an electron, he is going to be neutral. His charge is going to be 0 because his number of protons and electrons is going to be the same. All right, but now when he gives away his electron, he's got more protons than electrons now. And so after he gives it away, he's going to have a +1 charge. Again, because he has more protons than electrons. All right, if we take a look at chlorine, chlorine is on the right-hand side of our periodic table. He has high ionization energy and high electronegativity. So what that means is because he has high ionization energy, it's going to take a lot of energy to remove an electron. So he doesn't want to remove electrons. In fact, because he has high electronegativity, or the ability to attract other electrons to itself, he's actually going to be grabbing other electrons from atoms. So the chlorine atom is going to get or accept that valence electron from sodium. So if we take a look at before, chlorine has 7 valence electrons, and after, now he has 8, after he's gained that one from sodium. And so if we talk about the oxidation number, okay, beforehand, chlorine has equal number of protons and electrons, so his charge is 0, he's neutral. But afterwards, since he's got more electrons than protons, he actually has a -1 charge. Because remember, he's got one more electron than proton. All right, so we see here that afterwards, sodium has 8 valence electrons, and so does chlorine, and that's super important because atoms are going to bond in order to get 8 valence electrons in their outer shell, just like all of the noble gases. On the left here is a snippet of the periodic table, and we can see the noble gases. They are group 8A, that's this column right here. That means that all of them have 8 valence electrons in their shell, and we know that the noble gases are not reactive because they have full valence shells. Now, the only exception to the 8 is helium. He has 2, but remember, he only has 1 shell. So the first shell can only hold 2 valence electrons, so he is actually full himself. He is just a little guy that can hold 2 valence electrons. All the other ones are going to hold 8 valence electrons and be mighty happy. So, as we'll see in tomorrow's activity, noble gases have full valence shells and are very stable. And because they are so stable, all other atoms want to be like them in that they want to have 8 valence electrons in their outer shell. And so tomorrow's activity is called Noble Gas Envy because all the other atoms are envious or jealous of those noble gases. They want to be just like them. So I've been throwing this term ion around, and it's time we put it in our notes as a definition. So the third question is, what is an ion? An ion is an atom with a charge. So there's 2 types of ions. We can have a cation. Okay, that's how it's pronounced, cation, which is a positively charged metal atom. So in our scenario here with sodium and chlorine, to make sodium chloride, our sodium atom, okay, because it lost a valence electron, has a positive charge, and so it's called a cation. And chlorine, on the other hand, is what we call an anion. It's got a negative charge, and it's a non-metal atom. So because he has that one extra electron, it's going to make him negatively charged, and so he's going to be called an anion. All right, the fourth question we're going to handle today in these notes is, how can the periodic table help us figure out ionic bonds? Because I always say that the periodic table is definitely a work of genius, and here is another way that we can figure out ionic bonding from the periodic table. All right, the periodic table tells us the number of valence electrons in an atom by that group A number. So in group 1A, right, there is 1 valence electron. And so atoms in that group are going to lose their 1 valence electron, right? Remember, they are metal atoms, so metal atoms will lose valence electrons. Now, when they lose 1 valence electron, now they have 1 less electron than protons, and so they have what's called a +1 charge. And remember, any type of ion that is positive is what we call a cation. Now, group 2A, okay, often seen as Roman numerals as well, so you gotta get used to that. Roman numeral 2 has, again, 2 valence electrons, and because they are on the left-hand side of the periodic table, okay, so here's that 1A, and here's 2A. On that left-hand side of our periodic table, they have 2 valence electrons. Because they are metal atoms, they're going to lose those 2 valence electrons, and when we lose, become a positive charge. And because they lost 2 valence electrons, they will have a positive 2 charge, because now they have 2 more protons than electrons. And again, any positive ion is what we call a cation. Alright, as we move from left to right on the periodic table, remember the number of valence electrons trick does not work with our transition metals, so we're going to completely ignore those transition metals that screw everything up. Alright, and we're going to jump to group 3A, which is this column right here on the periodic table. Alright, 3A, right, means that there are 3 valence electrons. Alright, so we've got 3 valence electrons. Again, most of them are going to be metal atoms, so we're going to lose 3 valence electrons. It's all or nothing when it comes to ionic bonding. And when we lose 3, we become a positive 3 charge, and that's called a cation. Alright, when we get to group 4A, this group gets a little funny. Alright, because, let's see, 4 in Roman numerals looks like that. Okay, so again, they've got 4 valence electrons. Because they're kind of right in the middle, they can actually lose or gain 4 valence electrons. So it kind of just depends on who they are bonding with, if they're going to lose or gain. So our oxidation number can either be 4, a positive 4, if it loses 4 valence electrons, or it can be a negative 4 if it gains 4 electrons. So in this case, it could be either a cation or an anion. So it just, again, depends on who they bind with. Alright, creeping more to the right-hand side here, we've got group 5A. Alright, in Roman numerals, it's a big V. Okay, and again, group 5A is going to have 5 valence electrons. And now we're heading over to the non-metal side of the periodic table. Alright, we can see that in this group that it's mostly nonmetals. So remember, nonmetals are going to be the ones with higher electronegativity, so they're going to want to get or gain electrons. So group 5A is going to gain electrons, and they are going to gain 3 electrons, because remember, they want to get 8 total valence electrons, and so they are going to gain 3 more, because 5 plus 3 is 8. Now when they gain 3 electrons, they will have 3 more electrons than protons, so their charge will be a negative 3. And remember, negative ions are called anions. Alright, almost in the clear here. Next group is the 6A. Okay, so 6A looks like this in Roman numerals. And again, 6A is going to have 6 valence electrons. Alright, they are, again, the nonmetals, so they're going to want to get or take away electrons from metal atoms, and to get to 8, they just need 2 more, so they're going to gain 2. When they gain 2, they get a negative 2 charge, which is called an anion. Alright, almost done here. We're at 7A. Alright, so group 7A is going to have 7 valence electrons. Love the pattern here. Alright, they are so close to becoming like a noble gas, and so they are just going to gain just 1 valence electron. So when they gain 1, they're going to have 1 more electron than proton, so they'll have a negative 1 charge, and again, they'll be an anion. And our final group on the periodic table is the last column here, 8A. Alright, so 8 looks like this in Roman numerals. Remember, 8A means that they have 8 valence electrons, and because they are full and happy, they do not want to gain or lose any. Alright, so lose / gain 0. Alright, and so their oxidation number will be 0. They will be neutral in charge. Right? So they're going to be neutral, and so they are not going to be any type of ion because they're going to be neutral atoms. Alright, so we're going to sum up kind of what we just put in that chart in our notes, referring to the periodic table. Alright, so hopefully one thing that you notice is that atoms tend to lose or gain the number of valence electrons in order to get to the nearest noble gas to them. So if we're looking at beryllium here, okay, we can take a look at our periodic table and see, well, he could either gain 6 to become like neon or just lose 2 to become like helium. So it's going to be easiest for him just to lose those 2 because he is technically closer to helium than he is to neon on the periodic table. So he is not, I repeat, he is not going to gain 6. That's just too much work for him because remember, he's got low electronegativity on that left-hand side. So he is not going to gain 6. He is just going to lose 2 to become like the noble gas helium. Another example is selenium right here, Se. Now we can see that, okay, remember we ignore those transition metals, okay? So he can either lose 1, 2, 3, 4, 5, 6, okay, all the way over here to become like argon, or he could just gain 2 to become like krypton. So it's going to be way easier for him to just get 2 more. Besides, he's got high electronegativity. He's going to get 2 more to become like krypton instead of trying to figure out who the heck is going to give, or who the heck wants 6 of his valence electrons. So again, selenium is going to gain electrons to become like krypton here because he is closest to krypton on the periodic table than he is to argon. All right, hopefully another thing that you noticed was that metal atoms, all metal atoms here on the left-hand side of this staircase, remember, all those metal atoms are going to lose electrons to become positive ions. And the non-metal atoms on the right-hand side, okay, all of these guys are going to gain electrons to become negative anions. All right, and the last thing that we hopefully noticed is that when atoms bond, they are only changing the number of electrons that they have in their atoms. So it is not changing the identity of the atoms. We are not making or turning atoms into another atom. We are just gaining or losing electrons to become like the noble gases that have those 8 valence electrons in their outer shell. And so we are not changing the atom's identity like we were in when we learned about beta and alpha nuclear reactions. We are just changing the number of electrons in an atom. And the number of electrons is going, when the number of electrons changes, then we can make different kinds of bonds. All right, our last question of these notes is, what is a crystal lattice? Because this is going to be very specific to ionically bonded compounds. All right, so a crystal lattice structure happens during the formation of an ionic compound, where the positive and negative ions are packed into what's called a regular repeating pattern that balances the forces of attraction and repulsion between the ions. So let's take a look here at this picture. All right, here we have lithium chloride is the example. Okay, lithium chloride. And so the lithium is the metal atom. He's going to have 1 valence electron. He's going to lose that one to chlorine, okay, who has 7 valence electrons and is going to gain that one to get to 8. So the lithium atom is going to become a positive ion, and the chlorine atom is going to become a negative ion. And we can see here in this picture, right, that all of the positive ions are surrounded by negative ions, okay, because they're going to attract, and they are going to be kind of as far apart as from each other as possible because of repulsive forces. So in this crystal lattice, we have positive and negative ions packed in a repeating pattern like this, so that all of the positive ions are surrounded by negative ions, and all of the positive ions are as far apart from each other as possible, and the negative ions are as far apart from each other as possible. So the picture on the right-hand side here, okay, is probably when you want to draw into your notebook. And we can see if we say, these are all the negatives, the green ones are the negatives, they're as far apart from each other as possible, and they're all very close to the positive red ones. Okay, so that's what we call a crystal lattice formation. And sweet, that ends the notes for this time, and so we'll see you in class for an activity.